In this video, we will be discussing the concept of nuclear half-life. This is basically a measurement of the rate of decay of radioactive isotopes. We've already identified the fact that isotopes do break down when they're radioactive. What we're going to talk about now is that some atoms do this quicker and some atoms do this slower. Let's go over a quick list of the learning objectives of the video itself. The first question at hand is, what is half-life, or what is it a measurement of really? A lot of the way we explain half-life is through the process of graphing. We'll show graphs of atoms decaying at predictable rates. We'll talk about the shapes of those graphs and how they can be used. One of the questions I always get when talking about half-life is, why are we measuring the half-life? Why by the time for half of them to decay? Why not the whole life? And there's a very good mathematical reason for that. And last but not least, we'll talk about an application of this half-life concept, and that's carbon dating, a process used to determine the age of very, very old organic substances. For example, an old bone that you might find in the ground from a dinosaur, we can predict pretty accurately how old that bone is based on the number of carbon-14 atoms remaining in that substance. So let's start then with a question at the heart of the matter: what is half-life itself? Well, there's a couple of definitions we can go through. The first of which is a measure of the rate of decay of a radioactive isotope. As we've already said, radioactive isotopes do decay. Some of them decay faster and some of them decay slower. So half-life then is a measurement of that rate, how fast this process happens. Getting back to our idea of stability, the more unstable an isotope is, the faster the rate of decay. And this should make a lot of sense. If it's more and more unstable, the likelihood of the atom breaking down is much, much higher, meaning the overall decay process happens at a faster rate. Likewise, the more unstable an isotope is, the shorter, and this is getting back to our term here, the shorter the actual half-life is going to be. The less amount of time is necessary for that decay process to actually happen. So two things we can think of. More unstable equals faster decay rate, and more unstable means shorter half-life. Now, this might not be a great way of describing what half-life is, so there's another definition we can talk about. And half-life is really the amount of time needed for one half of your sample, one half of your radioactive isotopes to decay to form their actual product. And that's where the term half-life comes from, is the time it takes for half of them to decay. The unit then, as the last definition kind of implies, is a unit of time. And depending on the length of that half-life, it could be seconds, minutes, hours, days, or even years, depending on the sample you're dealing with. So to try and clarify this a little bit further then, I think it makes a lot of sense for us to actually look at a decay reaction and relate that back to the concept of half-life. So here's the decay of an element by the name of thorium. This is thorium-232. If you remember from our nuclear symbols, the isotope is identified specifically by the mass, which is shown up here. According to this reaction, thorium-232 decays to make radium-228, and it gives off an alpha particle in the process. So this is nothing new. These are the reactions we've been doing all along, except now we can add this new information in. We can say that the half-life of this radiation reaction, or of thorium-232, is 1.4 times 10 to the 10th years. And if you're not super duper hot with your scientific notation, this is basically 14 billion years, which means if we have a sample of thorium-232, say it's 100 grams of thorium-232, after 14 billion years, half of that thorium-232 will disappear. It'll change into radium-228 and give off its alpha radiation. So our 100 grams of thorium will now end up being 50 grams of thorium, and that process takes an extremely long period of time. Now, if you want to write that down, we have that same thing written down here in red. Every 14 billion years, one half of your radioactive thorium atoms will decay. They'll go away, and they'll give off the alpha radiation that they do and create the new, more stable nucleus, radium-228. So that takes 14 billion years. Now, in the next 14 billion years, we're going to lose half of our thorium atoms again. But remember, this time, we only started with 50 grams, half of our original supply, which means in the next 14 billion years, we're going to lose 25 more to get down to 25 grams. And then after that, next 14 billion years, we'll lose half of that, and the next 14 billion years, we'll continue to lose half of that. So this is what we're talking about when we're dealing with half-life and measuring with an actual reaction. To really drive this point home and to kind of wrap this up, what we have here is a graph depicting exactly the same thing. And we can see here this A naught is basically a measurement of the original amount of material that we have. And we can see at time 0 we have 100%. Oh, that's not a very straight line. But we have 100% of all of our radioactive isotope present. And after that time, after 1t, which is a measurement of a half-life, after one half-life is passed, now all of a sudden we've cut this quantity in half. We have half as much of the original material as before, and we'll say that's our original amount divided by 2. Now at this point in time now, we can think of this as a new beginning. We can say that, well, this is how much radioactive material I have now. As the next half-life happens, so now we have 2 half-lives have occurred, now we have half of the remaining stuff that we had from before left over. Likewise, we can think of this as a new beginning. When we get to the next half-life, again, half of the remaining material has decayed again. It's the original amount divided by 8, then divided by 16, then divided by 2. And we can see the decay rate of how fast these things go. If you know your mathematics and you've seen this thing before, this is an exponential decay function. And we'll talk about the mathematics in the accelerated level in a later video. But this, generally speaking, all of these graphs follow an exponential decay function pattern. Now we can turn the corner and stop talking about the definition of half-life, but instead talking about how we use graphs to understand and explain half-life. I know we've looked at the graph on the previous slide, but now we're going to talk a little bit more about where that graph comes from and how you can interpret it. So again, below we have 2 radiation reactions now. We have the beta decay of ruthenium-106, which is what we're seeing here in our first reaction. And we also have the beta decay of phosphorus-32. And again, these reactions should look very similar to what you guys have seen in previous videos and previous practice problems. The information we're going to add now then is going to be the half-life that goes along with each of these substances. In the first reaction, this process of the ruthenium breaking down into rhodium and beta is going to take 367 days. So every 367 days, half of my ruthenium breaks down, turns into rhodium, and gives off its beta particle. Another 367 days, half of whatever is remaining goes away, etc., etc. Same thing down below for phosphorus, but the only difference here is that our half-life is significantly shorter. In this case, it's only 14 days. Every 14 or so days, half of my phosphorus breaks down. What we can get from this is that these 2 half-lives tell us how fast this happens. The phosphorus breaks down at a much faster rate than the ruthenium does because it ultimately has a shorter half-life. And both of these have a much, much shorter half-life than the reaction we were talking about before. If you recall, that breakdown happened over the thorium, happened over 14 billion years. We're talking about things now that are happening in the span of days, so it's a big, big difference. Keeping those 2 reactions in mind here, we can actually use Excel to plot data according to this decay rate thing, and we can see those 2 plots side by side. First thing I want you to notice is that each plot has pretty much the same shape. And that's because, again, they are both exponential decay functions. So the shape of the graph never ever changes, but what you will notice is that they have different steepnesses to them. The ruthenium decays at a slower rate. On the x-axis we have our time data down here. So as a result we get a more gradual slope. We get fast decay in the beginning and we get slow decay at the end, but it's a flatter slope. The phosphorus decays much faster, has a much shorter half-life, and as a result we get a much steeper slope here in the beginning and we get down to those really low numbers much, much quicker. The shape is the same, but what the difference is the fact that the 2 different half-lives really relate down to the steepness of those 2 individual slopes. Last thing I want to say about this particular picture, we can also use this graph as a way of predicting the actual age of a sample. We can predict how long the sample's been doing this for. Looking again at our graph, we've got time on our x-axis and we've got percent remaining on our y-axis. So for example, if you have a sample that's giving off 30%, well, actually let's take it to this one. Let's say it's a sample that's giving off 10%, which is way down here, of the radiation a fresh sample would give off. We can use the graph then to predict that if this sample were ruthenium-106, it would give off somewhere in the vicinity of, it looks to me like about 1,300 days old. Whereas if this sample were the phosphorus-32, we trace to here, and this is very, very hard to make an estimate, but I would say that this sample is less than 100 days old. It's really hard to pin an actual number on that because it's such a small amount. But my point is by using some basic graphing thing, dropping down to the x-axis, we can make predictions as to how old a sample is, or likewise, we can make predictions as to how much of the material will be left over. And that's just really understanding graphs and working with your x and y-axis data. So before we move on to our last segment here, which has to do with carbon dating, I always get the question, why not whole life? Measuring the time it takes for half of the sample to go away seems particularly odd. And the answer to that question comes from the fact that, again, radioactive decay is an exponential decay function. And if you remember back from your mathematics class, this means a lot for the shape of that graph for us. It means we have very rapid decay in the beginning of the process. We saw those graphs were very steep, and we have much slower decay towards the end. And here's the real key point here, is that this slower decay gets slower and slower and slower the closer and closer we get to zero. The end result being that your sample never actually reaches zero. And we would say that this kind of a graph would be asymptotic, meaning if it never reaches zero, whole lives never really happen. Going even further, the amount of time needed because your sample never reaches zero would be ideally an infinite amount of time. So all samples would have a half-life of an infinite amount of time. If there's not a differentiation from sample to sample, then we're really not getting any useful information out of this data. The half-life is something all samples definitely go through at some point in time, and as a result, it's something more measurable. That's why we go with half-life as opposed to measuring whole life, and it has to do with the fact that we never get to the whole life. It's an infinite amount of time for that to happen. We can clearly see that again here in the graph if we focus primarily on the ruthenium plot, which again is this one here in the red-orange kind of color. We can see that our graph slopes down very quickly in the beginning. It starts to slow, and then as the graph continues, we keep kind of tracing along this x-axis line here, and it looks like it's super duper close, but if we were to zoom in, we would see here that it never really actually hits zero. The further out we go, the flatter and flatter it gets. So again, you never get to a point where all isotopes have decayed. You simply approach it more and more and more closely, but never get there. So again, measuring half-life would be impossible. Measuring whole life, would be impossible. Measuring half-life is something we can definitely do. So let's wrap this video up then by talking about an application of this. A lot is done with radioisotopes and their decay rates, but one of the most famous ones, one of the most well-known, is the process of carbon-14 dating. This is basically a method used by scientists to determine the age of some sort of living organism that has died. So for example, a dinosaur bone in the ground or some sort of human artifact, as long as it had been alive at one point, be it either a mammal or a walking organism versus a plant, as long as it was alive at some point, we can use carbon-14 to date it. What we do here is we measure the amount of a rare isotope of carbon that exists in these substances, that is carbon-14. It constitutes a very small percentage of the naturally occurring isotopes out there, but it's a radioactive isotope, which means it's something very easy for us to detect the presence of. When your animal is alive or when the creature is alive, the amount of carbon-14 present in a living organism stays relatively constant. We'll talk about why in a little bit. The amount of carbon-14 then after death decreases at a predictable rate. And this is really the name of the game here. Because it happens at a very predictable rate, it's something we can use as a mathematical tool to figure out age. So the amount of carbon-14 left then, after that predictable rate has occurred, can be used to calculate the age of our sample. Here's some more details in the actual process itself. On the left side of the picture here, we have a diagram depicting where carbon-14 actually comes from. So cosmic rays from outer space bombard our upper atmosphere. It creates high-energy neutrons that crash in with nitrogen atoms. And ultimately, the real important part here is that this whole process creates radioactive carbon-14. The assumption here is that we have a constant supply of this carbon-14 coming into our atmosphere. That carbon-14 then disseminates into our atmosphere. It's taken up by plants, which is eventually taken up by living organisms that eat those plants. So we get this constant supply of carbon-14 in, and then a constant decay of carbon-14 out because it's radioactive. And the end result is while living, the amount of carbon-14 here is very constant. Upon death, the eating part stops, right? And as a result of stopping, no more carbon-14 gain. Now is when we get the constant decay rate. Now is when we can start calculating how long ago that particular organism died. Just like before, we can see that plotted on a graph here. The half-life of carbon-14 is a very well-known number, somewhere in the vicinity of 5,700 years. As a result of that, we can plot on the graph how much of the stuff is left, or how much radioactivity is left in our sample versus the amount of time that goes along. And we can see that it's depicted over here in the picture. This stick here that was buried in the ground, when it just gets buried, it's got 100% of its radioactive material left, and we can measure this quantity of radiation being given off. After 5,730 years, which is the half-life of carbon-14, half of our radioactive sample has disappeared and is now giving off half the radiation. After another half-life, we get to 11,000 years, which is 5,000 twice. We have a quarter left, and we can have 12.5 left. We can again go back to this graph and say, okay, my sample is only giving off, like, say, this percentage here, which looks like about like 15% or so. I can trace that over here on my graph and see that my sample is a little bit older than 20,000 years. If you want to go further, we can certainly use mathematical equations here for this particular line, and we can pin that number not down to an estimate, but to an actual value itself. But again, because the decay happens at a predictable rate, depicted by this line, we can use that to predict the actual age of the sample. So that's pretty much it for now. If you're in an accelerated class, or we're going to go further with this in terms of talking about the mathematics, the equation I was just mentioning. If you're in my honors and standard groups, that's math we don't normally do, so we're actually done with the half-life concept. But at this stage in the game, you should be able to do a couple things. You should be able to describe what half-life is and what it really is a measure of. What are we trying to get at? You should be able to use plots of half-life in order to describe the process of half-life, what's happening to our sample, as well as to estimate the age of a sample. That's where we talked about dropping down a line to our x-axis to connect back to time. Last but not least, we talked about carbon-14 dating. You should be able to explain the basic principles of how it works, and again, relate it back to how it connects to half-life itself. If you can do all these things, you're in great shape. If not, you need to formulate some questions, and this will be something we can discuss in class.